In computer programming, there's a phrase, there's a word meaning over. The word is called overloaded, and that refers to something that has multiple meanings, to a function that can call out to a bunch of different places. So you can say print. Print is almost always overloaded. You can say print a number, or you can say print a string, or you can say print a string with numbers following it, and the numbers get plugged into the string. And so you don't really know which print is going to be called. And it, in a lot of cases, it doesn't matter. But the thing is that it's a whole bunch of different things. And the word love in English is overloaded. Love means so many different things in so many different instances. And this causes confusion and problems and all sorts of issues because you say, I love you, or I love pizza, or I love, well, I don't know, watching soccer. So, it's like you love these things, but loving a person is different than loving pizza, is different than loving an activity. And there's even other meanings of love. And the problem is that people get confused by them and equate them when they probably shouldn't. There's a Bible verse in Corinthians that's used for weddings, and it's love is patient, love is kind, love doesn't puff up, yada yada yada. But that's not the type of love that marriages are about. Marriages are about a romantic love usually, but the love is patient, love is kind in Corinthians is about a more giving a more giving love, a more perfect love. It's total sacrifice for the other person. It is, you know, it's doing all of these things while most people approach marriage as just romance and physical attraction. And so when you kind of equate these things, it's different types of love. And the Greek, which the New Testament was written in, Greek has different words for different types of love. There's eros, there's agape, there's philos, and I can't remember the others. Philos is brotherly love. It's like your love for your family. And so it's like, I love my brother. And it's like, yeah, we'll fight together. We'll fight with each other. We'll fight beside each other. We'll, and work together, a common bond, shared experiences, shared goals. And that's where Philadelphia gets its name from. It's the city of brotherly love. It was named after a city in ancient Greece, and Philos is the brotherly love. Eros is kind of the romantic love. It's the love between a man and a woman where they get together. And then there's agape, which is the love of God, which is the total giving. And so if you have this thing here where Diana says that she loves Anne, and Anne says that she loves Diana, that is more of a philos. That is more of a brotherly love that may go into the agape, where they want to give everything to make the other person happy. And yeah. Okay, so that's that. That's, them loving each other isn't them loving each other. But it is them loving each other, because love is this overloaded word that means so many different things. And English just sucks. I'm sorry. English is terrible. We have 50 words for one thing and one word that means 50 things, and it's just like a many to many relationship, and English isn't meant to be understood. English is meant to be barely understood. Let's put it that way. English is meant to be barely understood. Um, so yeah, that's kind of cool. And Anne comes up with this idea. She's like, okay, I'm not allowed to see Diana, and Diana's not allowed to see me. But we can go to school together. So Anne is willing to let her anger at the teacher, her rage at the teacher, her rage at Gilbert to just like simmer so she can see Diana, her friend, which kind of goes into the agape thing because this is something which is making her miserable. But, you know, she's grinning and bearing it, and it's like, yeah, I can do this, I can do this, I can do this. And, through gritted teeth, she's going back to school, and she goes by a different way because she knows that she can't stop and pick up Diana along the way because Diana's mom would see and there would be yelling and screaming. I mean, they aren't even talking to each other in school in recess. I mean, they could go out in recess and talk to each other probably, and no one or wouldn't get back to Diana's mom, but they're not doing that. They're just passing notes, so they aren't actually talking to each other. So, she's working around this, and she's also wanting to show up Gilbert, but at the same time, she doesn't want to admit that she's trying to show up Gilbert. And this reminds me of a line from one of my favorite movies of all time, Casablanca. So, Casablanca, you have Humphrey Bogart playing Rick. And Rick is kind of clever, and he's smart, and he runs a cafe during World War II in an occupied French town in North Africa called Casablanca. And there's this kind of low-life guy who smuggles and forges and does shady things for money, played by Peter Lorre. And Peter Lorre is great at playing this slimy sort of guy. And the character's name is Ugatti. And
whose character's name is Ugatti?
Thank you. Peter Lorre's character is Ugatti. And at one point, Ugatti asks Rick, and he says, "You do despise me, don't you, Rick?" He says, "If I gave you that much thought, I probably would." And, I mean, that just kind of, like, level sets the, I know who you are, but I don't really care about you enough to, like, hate you. And Anne is trying to go for this. Anne is trying to, I hate you, but I would hate you if I thought about you, but she actually goes for the I hate you. And so she's in this competition with Gilbert. And Gilbert, at one point where Anne just stomps him, beats him by 5 points, he's like, "Good job." And there's another thing where it's like, if your enemy hates you, bless him, and it'll heap coals on his head. Which is kind of what happened here, because Gilbert is like, "Good job, Anne," and Anne was like, "No! You're taking all the sweetness out of my victory. I wanted to make you miserable." And you're like, "Good job." And, this just blows Anne's mind, and she's like, "I don't know, I'm happy, I'm sad, why won't you be beaten?" And so Gilbert's definitely choosing the better path here. And it's next is geometry. And Anne is having problems with geometry. Now, geometry can be very tricky because, circles, squares, lines, all of that stuff is geometry. But the thing is that geometry is also a bunch of formal proofs, where it's formal proofs and formal constructions, and this is the way you do things. So it's like, okay, I want to find the center of a circle. So I draw a line somewhere through the circle. Doesn't matter where. And I have 2 points. where the line crosses a circle. And I use those 2 points and I find the middle of that line segment. And because it's a circle, the middle of that line segment, if you draw something that intersects the middle of that line segment at a right angle, it will go through the center of a circle. And this can all be proven mathematically because of distances and triangles. And if I had to, gun to my head, I probably could remember how to prove this. But that's Anne's problem here. She doesn't want to remember how to prove it. She just wants to draw the circles. She wants to imagine the circle as the lake of shining waters and the waves in it. She wants the lines to be a castle or a bridge or whatever. But anyway, so you find the middle of the line, the chord that goes from point to point anywhere on the circle. And that line goes through the middle of the circle. Yeah, the right angle to the bisector goes right through the middle of the circle. So now you have this other line that touches the circle at 2 points. And you know it goes through the middle of the circle. And because all points on a circle are the same distance from the middle of the line that goes through the middle of the circle is the middle of the circle. So you cut that line in half and you get the middle of a circle. And that's how you find the middle of a circle with geometry. And yeah, that's how you find the middle of a... And geometry has all of these proofs. It's like, this is how you construct a parallel line to another circle. This is how... Yeah, it's just all of these different proofs. And unless you're coming up with the proofs, there isn't very much imagination involved. And there are problems where it's like they thought it was unsolvable. One of the problems that people thought was unsolvable for hundreds of years, literally hundreds of years, was solved in the 2010s. And that's how to find a third of an angle. Now, it's easy to find a third of a line because what you do is you draw the line, you draw another line through a point, and draw another line through the end, and you mark off equal distances on the other line, and then you connect them as triangles, and then you draw parallel lines. And then so this one line that you made up, that you know the length of, that you broke up into 3 pieces, 4 pieces, 5 pieces, 50 pieces, however many pieces you need, because that breaks up and you have these similar triangles, because the similar triangles are similar, which means that they're scaled, one scaled to another. That means that this line, because it's a third of the edge, and that one means that one's a third of the edge. So you have these scaled triangles, and that's how you that's how you construct a third of a line. But the problem is that you can't do that with an angle. And I saw this proof, and I can't remember any of it. Apparently it goes on for 200 pages. It involves constructing 2 different angles, 2 different sets of angles, and then breaking it apart and then correlate. I can't remember it all. But it's a very complicated proof. And as I said, this is something that was solved recently. People 500 years ago were like, no, this can't be done. So, while it may not seem to Anne like there is much imagination in geometry, this is one of those things that's like, there's a lot of imagination once you get to the right level. Math. 1 + 1 is 2. 2 + 2 is 4. 4 + 4 is 8. And there's no imagination in that. These are just things that are. These are truths. But there's other things where it's like, okay, so here you have a bucket of balls, and there's 7 red and 3 white. So if you reach in and you grab a ball, there's a 70% chance that you're going to pull out a red ball. And then if you can pull out the next ball and the next ball and the next ball and the next ball. And the odds of what color the balls are depends on, the odds of getting a different color ball depends on what's currently in the bucket. So I pull out a red one, 70% chance that that's going to happen. I'm left with 6 and 3. That means there's a 33% chance that I'll pull out a white ball next, as opposed to the 30% chance that there was previously. Now, if I were to keep repeating this, the odds keep changing. So we have a 70% chance of a 30% chance, or a 70% chance of a 66% chance. And you add all of these different things up, and what's the odds of the last ball I pull out being red? And so you can take all of these different numbers and multiply them all together and add them all up to find out all the different possibilities where the last ball in the bucket is red. And there's sums to do this, and there's functions that you can use, and permutations and combinations and factorial. Factorial is a great function. It's a number factorial is the number times every number less than it. So you have 7 times 6 times 5 times 4 times 3 times 2 times 1. And this just grows insanely quickly. 3 factorial is 6. 4 factorial is 24. 5 factorial is 120. 6 factorial is 720. I mean, this just goes boom. But just like as I said, you have a 70% chance of a 30% chance. So this explodes in combinations and factorials. But the odds that the last ball you pull out of the bucket with 7 red and 3 white being red is actually the same chance of the first ball you pull out being red. Because if you're to pull out the balls, pull out all of the balls, line them up. And then you're saying, okay, now I'm going to reverse the list of the order. Reverse the list. That's a creative thing to do. And then all of a sudden, you have the first ball that you already know is 70%. That's the last ball. So this is one of those wild things where it's like you have this massive set of numbers, and it comes out to be 70%. And doing math, you look at these numbers, and if you're going to guess 0, guess 1. If you're dealing with circles, pi by 4, pi by 2. And these are just the guesses. If you're dealing with squares, square root of 2. 1.414. And these are just numbers that, it's like if you're going to do a random guess, pi. And it's kind of sad, but it works. And Anne thinks there is no creativity in geometry because she hasn't gotten up to the point of, there's all of these different things. There are these problems that people can't solve. Or people can't solve yet. Now, admittedly, you have to be super, super smart to solve some of these problems. And there are ones that people have worked on for years and years and years, and only finally recently have they come upon them. There's one called the 4-color map problem, which is really great, which says, okay, if you have a map, however big, however many countries, as long as they're all contiguous, which means that they all only are in one piece, not in 2 pieces. So you can't have like country being in 2 different places. It has to be connected. Like Russia. Very good. Yes, thank you, Lolly. Like Russia. So Russia is this big, huge country. And there's a little bit of it, Königsberg. Well, it's not called Königsberg anymore, but yeah, there's a little bit called Königsberg, which is disconnected from Russia. And it's surrounded by Poland, Lithuania, and Latvia. and it's disconnected from Russia. So Russia would break the
Well,
four
it is
color.
Russia.
It is Russia. Sorry, it is disconnected from mainland Russia. Or Alaska. Alaska is not connected to the United States. So Alaska would break the four color map problem.
Contiguous.
Contiguous is, what did I say?
You said the United States.
Okay. It is disconnected from the contiguous United States. So we have Alaska and Königsberg. And so we have these things that are disconnected. But if everything is connected and everything is all in one piece, then you only need four colors to fill this in. And they worked at this and they ground at this. And there are basic cases where it's like, okay, if the largest number of countries that touch a single country is one, which means that every country only touches one country, and you kind of have this bullseye situation going on. Actually, no, there you have two countries touching because you have one inside, one outside. But anyway, so that's a basic case where you have two countries that make up the whole map and they only touch one. And it's like, yeah, of course, you only need two colors there. And if you have three countries arranged in a triangle, they come together at a point with three. It's like red, green, blue. You're all done because red touches blue and green, blue touches red and green, green touches red and blue. So that's easy. Four colors, it gets more complicated because then you can go around the outside, but four countries, four colors, not a problem. Five, they did some tricky things where if you have five countries come together at a point, then they did some tricky things. And then with and anyway, they finally got up to this thing where it's like, okay, there's 1,000 different ways to do this in base cases. And they had a computer go through. It's like, okay, this is how you treat the all 1,000 base cases. And so they did a computer program and it drew all the different things. And they're like, yep, all of these match. And yes, it could have been done by hand. But that's long and tedious. And getting to the 1,000 cases, that takes the creativity. Sitting there with colored pencils going, not so much. Anyway, so there are creative things in math and geometry. You just have to get to the right point. And if you're to take a look at writing English, there's a lot of dull stuff in there. You have to learn how to spell words. And it's like, if you spell choose wrong, it's chose. And so it's like, there are rules and you have to follow the rules and know the rules. And then you can start using things to build creatively. Math has just been studied so long and so hard. I mean, math has been, well, because math is math. It's like, oh, this is English, this is French, this is German. The rules in English, French, and German are all different. And Latin and Sanskrit, Hebrew, all of these languages are different and all have different rules. But math is math. Pi is 3.1415926535896 all the way to the end. No matter. Very good, Lolly. Pi has no end. Anyway, has however many decimal goes on forever. But the thing is that it's always the same number. It's always the 3.14159. It's 3, 1, 4, 1, 5. So, it's always that. 3, 1, 4. I can't remember much Spanish. Let's see. Yeah, trois, un, quatre, un, that's French. And, so all of these different, it's the same number. It doesn't matter. It's 3.14159, etc. forever. And it's always the same number. And so math is math is math. The dividing of a line into three parts. Or dividing an angle into three parts. This is something that stymied Pythagoras. And Pythagoras was like 4,000 years, 3,000 years ago. So this stuck Pythagoras, and Pythagoras is like, no. But they finally have a proof, which is just like, this is something that they've been working on for 3,000 years. And so, math is math is math. And so there's all of the basic stuff has been found, or most of the basic stuff has been found. There may be something coming up where it's like, oh yeah, here's this new type of math. And everyone was like, wow, we didn't think of that one before. Like set theory is a fairly new thing. Graph theory. Graph theory is actually what the four-color map problem is part of. You'd think it's geometry because it's all about shapes, but it's graph theory because it's about the connections of places, because it doesn't matter that the line is squiggle or straight or round or bent. It just matters what touches what. So you have a connection, set of connections. But that's geometry. That's all of these different things that, types of math that haven't been around, but at the same time, it's still math. It's still logic, formal numbers. Logic, formal numbers.